on va faire appel à Rashid Waraich, voilà, qui est donc chercheur, spécialiste des transports à l'École Polytechnique de Zurich. Et on va essayer de l'interpeller un petit peu sur... là, on va peut-être revenir un petit peu sur les questions de modélisation et de voir un petit peu si les approches françaises ont des points communs finalement avec d'autres approches internationales ou si elles sont très différentes. You are a transport specialist in the Swiss Federal Institute of Technology in Zurich. So we want to say, have the French approach common points with the international approach in modelization, or are they very different?
Thank you. So, good afternoon. Currently, I work as postdoc and lecturer at the Institute for Transport Planning and Systems at ETH Zurich. And currently, and today, I will present you some of the results from my dissertation. So, related to parking. So, why do we want to model parking? The main kind of motivation is that we want to design parking policies and we want to have models which help us during this process. And parking, it's one of the main ingredients if you want to really manage travel demand in a city. And it can, for example, act as a complementary or even as an alternative to road pricing sometimes, or to other taxation measures. When we look at cities, often what you find is that you have minimum or maximum parking requirements. I mean, this varies quite a lot, for example, between the US and Europe. And also there you want to provide models which help you to, with possible implications of change to current laws. Parking search traffic, it's often ignored in many traffic models, but there are several studies around the globe which suggest that, that on average, like 30% of the traffic around city centers, it is due to parking search traffic. So we want to also kind of try to model this traffic. When you have new infrastructure projects related to parking or even or changes, you want to kind of model possible implications of that. If we look at recent developments, what we see is that with the advent of smartphones, the transaction costs between people have dramatically been shortened. So it becomes extremely easy for people, for example, to rent their private parkings for a couple of hours, which is also happening in various cities. So now the question is, I mean, if you allow this to happen, I mean, what are the possible implications of this? For example, if you look at Zurich, only 1/4 of the parking in the city there belong to the city, and most of the parkings are private parking. So basically, you can think about how big an impact this could have. And you want to have models which allow you to look at possible scenarios in this regards. Performance-based pricing. Perhaps you are aware of the project in San Francisco. There is a project called SF Park. They have basically put sensors on several thousand street parkings to measure their occupancy, and they actually look at this occupancy, and at the end of the month they change the prices for the parking according to demand. Okay, so if you want to implement a similar system in your city, probably perhaps you don't have the budget to try it out first and spending a couple of $1 million. So you need models for doing that. And one of the other important things also is electric vehicles. This is actually was the topic of my dissertation. So if you have electric vehicles, what kind of, I mean, you can really naturally use parking to promote electric vehicles if you want, or also, I mean, there are connections, for example, for charging in there. Okay. So if we look at current models for parking, we find is that many of the current models, they are aggregated in terms of both time and space, and often the individual decisions, they are either missing totally or limited. And the integration between the transport simulation and parking is also missing, and this is very important because, for example, if you want to, for example, see what changes in parking supply or prices or whatever they should be basically, they have an implication mostly on the traffic demand to an area, and this is in most models which are out there, this is ignored at the moment. Okay, so to start this modeling activity, the framework we are using is called MATSIM. This is a framework which has been developed at ETH Zurich and TU Berlin. And basically, MATSIM, it's an agent-based travel demand simulation framework, meaning that you're trying to model the activities of the people throughout the day. So real people in the real world, you try to represent them as agents in your simulation. And these people, they are performing activities. In order to get between these activities, they need to travel using different modes. Here you see cars, and of course they interact, and possibly you have traffic jams and so on. So, okay, so if we now go in a little bit more detail into MATSIM, what it does, I mean, MATSIM, it's an open source framework, so if you want, you can download it and use it. In MATSIM, people in the real world, you try to represent them in your model. You find out, based on, for example, census data, you find out where people live, what kind of people live where, what kind of properties they have, like income, gender, age, and so on. And based on travel diaries, you find out what kind of trips distributions they have, and what kind of activity chains they perform. So and also the preferences of these people, you try to really, based on surveys, you try to model the preferences of these people in your models. So I will give an example later for that. So now you have plans for these agents, meaning that where they are at home, where do they work, and so on, and they basically can use different transport modes for traveling between these activities. And so if you introduce some kind of change in your system, you can see how these agents might probably change their behavior. So the goal of this whole process is basically, it's an optimization for each individual. So, and you can see that it's an iterative process, and with the first step is the simulation. The simulation, this is actually what I have shown you before in the video. It is the first step where you actually perform a full day simulation, like people in the morning, they're waking up, they're going, perhaps taking a bus to go somewhere, to work or something like that. So as this happens, you have interactions between these agents, for example, in the traffic, and you can possibly get delays. So after this simulation, you actually score your, the simulation result. So if you have a lower travel time or you can perform longer activities, you get better score. And the goal is kind of to maximize the score of your day. And in order to do this, you have a replanning step. This means you can adopt your plan. For example, you can change your travel mode, you can change your route, you can change the departure time, or in my case, probably your parking. And with this, you try to improve your score. So actually, it is evolutionary algorithm which is plays behind this. So you can say that with plans with a higher score have a higher chance of survival than those with a lower score. And in the end, what we're kind of trying to get to is a Nash equilibrium, meaning that no agent can unilaterally improve its score. Okay, so basically I will now present two models which I created. The first one is a parking choice model, and the second one is a more recent development, a parking search model. So the parking choice model works as follows. Let's assume in the beginning, you have your destination is in the middle, and you want to park there at a certain time of the day. So first of all, basically the parking choice set is huge, I mean, in the beginning. So first of all, you just discard things which are too far away. Then what you do is you kind of remove the occupied parkings. You remove the parkings which this person cannot use, for example, private parkings of a certain kind. And then what you do is you use a utility function to assign a score to each of the remaining parkings. For example, this utility score, it depends on the parking costs, of course, and also, for example, on the walk time. For example, if you have to walk longer, it gets more this utility. Okay, and so in the end, there are different ways, but you can, for example, you select that parking which gives you the highest utility. Now, if we go a little bit more in detail about this scoring function, the scoring function, where does it come from? I mean, the scoring function comes from stated preference choice surveys. So if you look at, for example, this is a real kind of the result from a survey from Switzerland. If you have a parking situation where, I mean, for example, the walk time is 3 minutes, parking cost is 4 Swiss francs, and so on, two different people can react totally different, and their weight of the different parking components can be totally different. So, for example, this man who is 80 years old weights, for him, this utility for walking is far bigger than for the young woman. Okay, so when we get this parking score, what we do with it is we add it to the overall utility of the plan, and this is actually the place where you integrate the different choices of the agent. For example, now what happens is if you have an area with where there is a scarcity of parking, or the parking prices are high, it becomes not attractive for the agent to travel there with cars. So it probably, if you have a different travel mode, or even if you decide to shop somewhere else, this might be more attractive for this reason for you now. To give two examples, let's say you would like to reduce peak traffic in an unconventional way through parking. Supply reduction. So what you could do is you could look at the peak demand or the the evening peak for the traffic, and you can really find out the highest volume links, traffic volume links. You can find out where are these agents coming from or going to, which travel during peak hours on these links. And if some of these activities are happening in the city of Zurich, you can kind of form clusters and start reducing the parking supply in those areas. For example, by 30% and 100%. So alternately, you could also increase the prices. So what you see is actually that the traffic on these highest volume links, it goes down, but you also see that various other things happening in the other hours of the day. And this is just to remind you that, I mean, a traffic system, it is quite complex. You cannot assume that if you reduce some supply that probably, I mean, it is that the demand is really going to go down. It might go even up at other times of the day. Okay, so when we also looked at performance-based pricing for Zurich. So at the moment what we have is we have very high prices for garage parking in Zurich and rather low for street parking. So we were just wanting to replicate the experiment from San Francisco for Zurich. So if you would really allow markets to play, what would happen with these prices? So what we see is that most of the garage parking prices, they go down, and the street parking prices, they increase. This is, I mean, it is plausible because, I mean, many of the street parkings, they are located closer to you sometimes than the garage parking. So in principle, your willingness to pay for them is higher than for the garage parking. But of course, with these kind of experiments, you can also look at the other thing, that how does the overall revenue of your system change? Okay, so now let's look at parking search. In general, when we look at parking search, I mean, it is a quite difficult process because basically what we decide on is not the actual parking, but we decide on the strategy when we are looking for a parking. So if we approach a parking, and this is how in the research literature it is described, is when people kind of approach a parking, what they kind of try to do is they can take a proactive approach, and either they can reroute from the shortest route to find a route which, with high probability, gives them free parking, or they can, if they know the situation a little bit of this area, they can straight go to an off-street parking. If they reach the destination and they don't find a parking, sometimes people do illegal parking, or they go to an off-street parking afterwards, or they circle around. So you have various strategies in the literature reported. And what we did is we took 10 of these strategies, which kind of have been how people do parking search in the area of in Germany. And what we found is that if you start giving our agents the certain options, for example, these 10 different strategies, they as the simulation iterates and the simulation goes on, most of them find certain certain strategies which render them a very high score, and this solution is mostly unique. But sometimes you have more than one strategy which gives them similar scores. But of course, I mean, these results, you would have to validate this how the situation in Switzerland is. We haven't done that yet. And of course, you can produce with this how the traffic changes due to the addition of this search traffic to the base traffic. So you have really roads which around the city center of Zurich here, which have a lot of additional search traffic and also other changes in the system when you consider parking search traffic. And also some strategies, parking search strategies, they are used more often in certain areas of the city. Naturally, for example, garage parking related strategies, they are used for reaching destination around the city center. So to conclude, I've presented a model for modeling parking decisions and parking search with a disaggregated model, which is an iterative equilibrium model. And as I've shown various, in the motivations, during the motivation, that there are various applications of such models. And I've shown some examples of how this could be done. So probably we will continue working on such applications. Thank you.
Thank you very much.